Chapter 9, Section 10, Completeness. In this section, we will explore the concepts completeness, Cauchy sequences, and convergence. These concepts are important to understand some machine learning algorithms such as support vector machine. Let me start with a simple but important question. What does it mean for a space to be complete? In previous lectures, we have talked about inner product spaces, vector spaces equipped with an inner product that defines angles, length, and projections. But today, we introduce the missing ingredient that makes these spaces even more powerful, especially when we move into the infinite dimensional world. That ingredient is completeness. Completeness helps ensure that when we work with infinite processes, like approximating solutions or summing infinite series, we do not fall out of the space we are working in. Let's begin by looking at the definition of completeness. A metric space is said to be complete if every Cauchy sequence in that space converges to a point within a space. At first glance, this definition might seem quite difficult. However, if we break it down and examine each concept involved, the meaning behind the definition will become much clearer. So, let's now take a step-by-step look at what this definition really means. To understand completeness, we first need to talk about a Cauchy sequence. A Cauchy sequence is a sequence where the elements get arbitrarily close to each other as the sequence progresses. Formally, we say that a sequence xn is Cauchy if for every small number epsilon is larger than 0, there exists a point in the sequence, call it n, such that for all m and n are larger than n, the distance between xm and xn is less than epsilon. Intuitively, this means that the terms are clustering together more and more tightly, suggesting they are heading somewhere. Let's look at an example of a sequence. The terms of this sequence are gradually getting closer to 2. Also, the distance between the terms is getting smaller. The terms getting closer to each other, in other words, they are clustering together. It suggests that the sequence is heading toward the same point. However, a Cauchy sequence does not necessarily converge unless the space it lives in is complete. Imagine working toward a destination by taking steps that get smaller and smaller. Half the distance, then a quarter, then an eighth, and so on. You are clearly approaching something, but if the space you are working in has a hole at the destination point, you will never actually arrive. That is what happens in an incomplete space. The limit exists in theory, but not inside the space itself. Now, in complete spaces, every Cauchy sequence does converge to a point within a space. Let me show you a classic example that illustrates this clearly. We will compare two number systems. The real numbers R, and the rational numbers Q, that is, numbers that can be written as fractions. Consider the following sequence of rational numbers. This sequence is a Cauchy sequence. The terms get closer and closer together as the sequence progresses. This sequence is also approaching the square root of 2. In the real numbers R, this sequence converges to the square root of 2, which is a real number. Since R includes irrational numbers like the square root of 2, the limit of the sequence is part of the space. This shows that R is complete. In contrast, the square root of 2 is not a rational number. This sequence does not converge within Q. Even though the terms get arbitrarily close to each other, their limit lies outside of the rational number system. That means Q is not complete. So, even though the same sequence is Cauchy in both Q and R, only R is complete because it contains the limit. Now, let's go back to the definition of completeness. A metric space is said to be complete if every Cauchy sequence in that space converges to a point within a space. In other words, if we are working inside a complete space, we can safely use sequences that get closer and closer together, because we are guaranteed they will arrive somewhere in that space. If a space is not complete, some Cauchy sequences might aim toward a point that does not exist inside the space. So, again, a Cauchy sequence is one where the elements get arbitrarily close to each other. A convergent sequence is one that actually approaches a specific value, a well-defined limit. Completeness is the property that connects the two. It ensures that every Cauchy sequence truly converges to a point within the space itself. In a complete space, getting closer and closer always leads us to a real destination within that space. Thank you for watching. Please thumbs up and subscribe to my channel.